Welcome to another episode of the Nuclear Medicine and Molecular Medicine podcast. And as you can tell, I'm recording from home. And many of you might be at home now. With this terrible COVID crisis, we need to work together as a community, care for our colleagues, and make the most of this time. And part of that is I'm going to be increasing with the frequency of the podcasts and with information that's useful for all nuclear medicine professionals. In particular, if you're going to be presenting at a meeting that's been cancelled, there's been a lot of meetings that have been cancelled, there's probably a lot more, get in touch with me and we can record a meeting via Zoom, and then we can present that, your presentation or an interview or both, via the podcast. And the same is for organisations. We're looking at doing something similar with the Australian-New Zealand Society of Nuclear Medicine, the US Society of Nuclear Medicine, the European Association of Nuclear Medicine. If you want to make use of my resources to help you get your message out and make good productive use of the time that a lot of us are going to have in the upcoming weeks and months, perhaps, that I can help you. I'm certainly here to help you. So you can email me at rob@nuccast, nuccast.com, or at my work, that's williams.r@unimelb.edu.au. So we're going to be making good use of this time. A lot of it is about writing papers, a lot of it is about processing the data that we've already accumulated, and part of it is planning for the future. It's unfortunate this has happened at such an exciting time. There's so much that's happened in the world of theranostics. So much is happening in the world of therapeutics in general, for cardiac, for neurology. Let's not waste this time, and let's get ready to get back into work as soon as possible. Anyway, I'm going to talk to you now with a podcast with Dr. Slomka from the San Diego meeting, the last Society of Nuclear Medicine meeting, where we're dealing with artificial intelligence and using AI for all sorts of reasons. I think that's a really exciting way that we can use our existing data, and also the way that we can go forward in doing lots of things. And he's talking about how to use it in the rest-stress situation, or the stress-rest situation for cardiacs, so that you don't need to do a resting cardiac. That way, reducing the need for extra radiation doses, and using AI to give you a ballpark answer that says, really, we don't need to go any further. This stress has already got enough information. So I'll get onto that now, and keep in touch, stay safe, and let us know how I can help you. Thanks, bye. Okay, welcome to another episode of the Nuclear Medicine, Molecular Medicine podcast, and we're here in Anaheim in California, and at the Society of Nuclear Medicine meeting. And I'm talking to Professor Piotr Slomka.
Yes,
and he just gave a very interesting talk on artificial intelligence and cardiac imaging. We haven't talked a lot about, we've talked about artificial intelligence before on the podcast, but we haven't looked at it in the aspect of cardiac imaging. So first, perhaps you could just introduce yourself and tell me a bit about yourself.
Okay, thank you very much. So my name is Piotr Slomka, and I am a scientist and a professor at Cedars-Sinai Medical Center here in California, in Los Angeles, and a professor of medicine at UCLA. So my background is technical. I work with computer engineering, and I develop various algorithms to improve diagnosis and prediction of events from cardiac imaging, and in particular from SPECT, PET, and CT. So that's what we do.
Yeah. So you showed us how artificial intelligence can be used, and one of the one way that's been talked about a lot is how to reduce improve the throughput and reduce the radiation dose by avoiding the rest aspect of myocardial perfusion scanning. Can you explain a little bit about how that works?
Yes. So nuclear cardiology is a very commonly performed test for diagnosis of heart disease and for prognostic purposes. And the nuclear cardiology test consists of stress scan and rest scan, and that is to because we try to estimate the amount of damage in the muscle or amount of stress, amount of hypoperfusion in the muscle which occurs during the stress, but it's not there during rest. But about 80% of the scans are actually normal. So in those scans, the rest scan is actually redundant. So, but currently only maybe few percent of the labs are actually implementing technique where they are canceling that redundant rest scan in the case of this normal stress scan. And this is because to cancel it, the clinician has to decide at the very time of doing the scan that the scan is actually normal. This is logistically very difficult, and it also includes looking at the clinical variables and so forth. So in a way, this presents a perfect application for AI, where we could, during the scan, technologist who performs the scan who could run this program, and the program will tell that rest scan is not needed in that case, and the patient would not receive additional dose, and the patient would also could go home earlier, saving time and resources. So basically, this is an application which we've devised. We show that it actually can outperform, even if the clinician were available and do it, it can actually outperform in terms of diagnostic safety, in terms of predicting if this scan is truly normal or if these people actually have some underlying disease.
Well, not only is it outperform it, but it's a situation where people have been nervous about using AI, right? They've been nervous about whether it's going to produce false outcomes and so on. This is a very safe application because there's no real downside to this. If you don't need, if they do need to come back, they can always come back and have a rest scan another day, right?
Exactly. Because, for example, if the clinicians would come in the evening, would look at the scanners, and they say, no, actually, I really need that rest scan, they can call the patient back, and in those unusual cases, the patient could come back. Maybe it's a little more complicated for the patient to come back, but it's not going to occur very often. And so the bar is not as high as actually performing the diagnosis by AI. It's only to say that rest scan is not needed.
So how many cases have you done with this?
So in that study which we've shown here, we have over 2,000 cases, and each of these cases have disease verified angiographically. So this is all retrospective. We're not actually using it prospectively clinically right now, but we're testing what would happen if we canceled. So we actually have the rest scan, but the AI is not using the rest scan for anything. It's only using the stress portion, and then it's showing that it can actually predict only from the stress portion how well it can predict. Whereas the clinician actually, the data we have has everything there. So we have over 2,000 cases, and in those 2,000 cases, it shows that the amount of disease it predicts is with a higher sensitivity than a clinician would have predicted. So meaning that it's safer to cancel the rest scan than if the clinician would do it.
Right. So have you got any idea how many people might be called back to have a rest scan?
So it's using, so depending on the threshold we set, like how safe we want to be, we can cancel a different number of people. So we actually now are doing, we will present this later in another meeting, but we have another 20,000 cases in which we are testing this. The range will be, depending how safe you want to be, is from 30 to 60% of the scans can be automatically canceled.
Right. So that's significant. That's a significant saving, not only in cost but also radiation.
Yeah, of course.
The other thing you showed was ancillary purposes was using artificial intelligence to interpret a calcium score from the CT from SPECT CT.
So this is work. Actually, this is the work which Dr. Ivana Izgum in Holland is taking a lead on, is doing that work. So there's a few papers they published automatically detecting calcium scores. And we had one paper with her showing that we actually can detect calcium score using from attenuation scans.
Right.
So there's so calcium scores are usually done from the CT scans, which are high quality. They're gated. but actually it's possible maybe that they can be done from the attenuation scans.
Right.
So we plan to collaborate with that group on this. And we also look at from the CT, our group works on the percardial fat, looking at the CT, the fat which is inside the percardial fat, and that in the percardial sac, and we can automatically quantify this data, which actually is included in every calcium scan, but yet it's not reported and not looked at because it takes about half an hour to derive to segment those content.
Right. So you're basically using the artificial intelligence as a labor-saving device, right?
It's like saving the time which experienced clinician will have to spend to actually get the volume of that fat.
Right, so you're getting information that you otherwise wouldn't have got. Another case where it's a very safe application of artificial intelligence.
Yes.
The other thing you showed me, which I thought was really interesting, was was using a D-spect, which doesn't really have the attenuation correction, but you're doing two imaging, prone and supine, and comparing the two. And a lot of people have trouble figuring out, is there a difference when you do it prone and supine? If there is a difference, then you know that the lesion is caused by attenuation. If there isn't a difference, then we know it's a real lesion. But still, some people have trouble with that. How does artificial intelligence help there?
So here we think is one of the also very good applications for AI, because the deep learning also have difficulty sometimes with the amount of data and how well it can be trained. But in nuclear cardiology, we have polar maps, and polar maps can be fed directly into the deep learning network. And we can actually feed the upright and supine polar maps from two different positions. These polar maps will show defect a little differently in the different locations. And between those two, if there is a defect and the maps look a little different, and then we can train the deep learning network on the outcome of the obstructive disease. So system will show us, what kind of situations it actually is very likely that there is a disease in a particular location versus not. So in a way, it's the deep learning network allows us to combine those two views in a way which enhances the diagnosis.
Right.
So that's the application here.
Right. The deep learning's better in a three-dimensional way to actually map two images. That's really what's happening, isn't it?
Right.
Whereas the eye has a little bit of trouble with that, and because it uses the polar map.
Yeah.
But it's also interesting, I think, that we're using a polar map, and that was originally used for the first sort of computer score for reading how many years ago? 30 years ago?
Right.
Right, so it's amazing that that's come back again and being used again that way.
Well, the polar maps are used by the clinicians visually, so in a way that was our first thought that we will also use them in deep learning maps. I think when we actually want to predict one outcome from the whole for the patient, it's just not enough data, not enough cases to train on the whole 3D gated, ungated stress and rest images. It's much easier to do polar maps. That's not to say that in the future maybe we will actually use the raw images and see if that improves things. But right now it seems very rapid application. The training for this takes maybe only a few hours to train the system and to execute if this is we have already implemented it in our quantitative software, it takes only 1 second to compute and provide the risk.
So your software is already available now. People can already use it.
So that software this is a research version right now. We are working on providing it actually a commercial version. Right now this is something we can use it on a research basis.
Right.
Yeah.
Excellent.
It's available. It's implemented. It's something which clinician could try and see how this works.
Right. So what commercial do you know where it's going to be commercialized? So
Cedars-Sinai licenses the quantitative software, and we hope that this will be part of the package will be a module where it actually enhances the diagnosis by those kind of new approaches.
Excellent. So, I mean, most people who are doing cardiac work would have access to a Cedars-Sinai package, right?
So that will be just an add-on and a way, to show that, that for the clinician to show that enhanced, in this case, diagnostic prediction of likelihood of obstructive disease.
Right. So I think what's a bit useful here is all of the stuff you've given us in all of the things that you suggested were things that are virtually zero risk implementations of artificial intelligence, and people were worried about that it's going to give wrong diagnosis and so on. But the things that you're talking about are really enhancements of information that's already
I think we look at it as just enhancement of accuracy of what we already have. So the clinician will be given some new result, and then clinician can decide if it's correct. And most importantly, everything we do will provide the explanation of how the network, even the neural net, how it arrived at this diagnosis. So in case of the when we predict clinical risk, we can show which variables for a given patient were actually significant. Clinician can then decide if this is true.
Right.
And in case of images, we actually can show on the polar map
right.
what parts of polar maps are actually responsible for the final finding.
Right. So you've got the polar map, and then you've got an overlay basically on that,
right, where we show like that those parts. So if it was an artifact, let's say, and I think this is very important first of all from the comfort level of the physician and safety, that the clinician can review this and see that, okay, well, I see that something could be there. Or if it's like a blatant artifact, somehow the network was trained in such a way
right.
that, then they will see, okay, well, that is triggering by something which makes no clinical sense. So that final clinical knowledge will be always there,
Right.
It will be
so if you've got,
this.
a funny diaphragm or something
it can
like
have,
that.
because we have to. The systems are very powerful, but if they are presented with cases which they have never seen before, they will fail. This is no. So those cases which, if we didn't have particular examples in the 2,000 or 20,000 cases we have, if those examples are presented, they will probably give incorrect answers.
Right.
So that's why you need to show and explain to the physician how even the things like a deep neural network, how it works actually.
Right. So the physician becomes his expertise. It becomes even more important because it's about picking what's wrong with an image.
I think it will just enhance the capability of the physician. That's how we look at it.
So we take the boring bits out and put the interesting bits in.
I think it will enhance the accuracy, and it will give them more power in. And it will basically, one quote here was one of the speakers said that you will do more with less, and I think that's something we do in nuclear cardiology also. We try to get more from the simple images, or maybe lower dose images, or maybe from stress-only images. We try to enhance as much information as possible and give it to the physician to then enhance his capabilities.
So this basically means that the perfusion image has a new life, if you like, because it's provided. You're getting calcium scores, you're getting the fat score, we're getting deep learning. There's been a push somewhat to do other types of imaging, to do CT and so on, or ultrasound instead. Maybe this is going to give a superpower boost back to the myocardial perfusion scan.
I think so, but I think obviously in CT and ultrasound they also work on the same things. But in a way, it will be in a way it will be fair if we try to enhance everything what's possible from a given scan and see how much information it actually is, and then we can really compare if the CT is better or not.
Right.
Whereas otherwise we may not compare the most optimal way SPECT is done, but it's certainly with enhanced SPECT, and we'll certainly be able to get more done. And the question is that going to be better than CT? That we'll have to see. But I think we have to give it a fair chance, and if the technique is cheap, available, and we can do more with it, then we should try. So.
That's fantastic news. Thank you. Very, very interesting. Anything else you want to add or put in?
Can you? Sorry.
Anything else you'd like to add in terms of?
No, I think. Thank you for this podcast. Was arranged sort of impromptu after my talk, but
it usually is.
Yeah, but I'm very glad we can communicate this.
Right. Thank you very much.
These ideas. Thank you.
Thank you.